Friday, happy June, everybody. Know it's June, we're getting close to the end. We're on to the second of the written assignments and the last programming assignment now. I want to make a couple logistic notes about PA8. Which is about optimization. So PA8 is going to be a little more open-ended than some of the previous assignments. In the previous assignments, we sort of said, here's a language, here's a specification, make that happen. For the optimization assignment, we've talked about a number of optimizations. We've talked about register allocation, instruction selection, p-pole optimizations, constant folding, constant propagation. There's common sub-expression elimination that we introduce and talk about in the written assignment. There's a lot of optimizations. You may even have followed some links and read about other optimizations that you think are interesting. So the way PA8 is set up is that we give you a compiler and some programs, and you change the compiler keeping answers and effects the same, right, our definition of optimizations. And those, programs get better. And we have two criteria for better that we're going to test on. One is number of instructions generated for each one of the programs, and the other is runtime of some of the programs that have loops and run for longer. And the exact number will be we're deciding on the exact number of programs that we're gonna give you to work on. But the idea is the compiler should pass all the same test cases. There should be no program that produces a different answer after you do this. But there's going to be some bounds. We'll expect that you get some of these programs down to half of the instruction count that they were on the original compiler we give you, or down to half of the runtime that they take with the original compiler that we give you. And your grade will be based on making some number of them some amount better on these metrics. Okay? And you can pick any optimizations that we've talked about that you want. We've given you sort of starter code and descriptions of how to do different ones of the optimizations we introduced in class. But it's up to you what to do and to decide when you're done based on the criteria we set up. Okay? And all the optimizations we talked about will be useful for some or all of these programs. Any questions about the setup for this? It's also open collaboration. What I hope happens here is that people try things out, say, this worked really well on these programs, you should try this, you should try constant folding for these programs. You can post that on Piazza, talk about what works and what doesn't. Questions about the setup for this? Does it sound fun? Yeah. Yay. Okay. All right, cool. So that's what PA8 is going to be like. In terms of lecture content for the rest of the quarter, so today I'm going to talk about type checking. That's what today's lecture is about. And next week I'm going to talk a little bit about some interesting things we can do with functions. And then I'm going to have a couple lectures, the last two lectures. If people have any suggestions of things they want to hear about in compilers that we haven't talked about yet, some of the questions during quizzes have asked about things going on in modern compilers research. I'd be happy to take suggestions. I have a research topic that I'm interested in talking about during lecture, so I'm probably going to take one of next Wednesday or Friday and talk about compiling things to run in web browsers, which is something I do research on and has some interesting challenges related to the way we've been compiling things, which is compiling things just to run on a sort of traditional desktop operating system in a traditional operating systems process. It's actually different assumptions you have to make and different things you have to do if you want things to run, if you just open up a Chromebook and want a compiler to run within that web browser. It's a different compilation target. But I'd be happy to hear suggestions. If you want to do them as private Piazza posts or any other way, shoot me an email for things you want to hear about. I can't guarantee I'll do anything and everything that you suggest, but I'd like to hear if there's some common thread of something that people are interested in hearing about. Okay. So today, type checking. Monday, we're going to talk about first-class functions and closures, which are vocabulary words you might have heard of that have to do with compiling interesting things about functions. And then Wednesday and Friday will be review and some research topics. All right, so if that description of what's left out something you had burning desire to hear about in a compiler's class, let me know, because maybe we can talk about it a little bit next week. All right, so let's talk about types today. Let's talk about type checking. I mean, I have type checking as sort of the umbrella concept here. And what our compiler does right now in terms of looking for errors, type checking is going to have a lot to do with looking for errors, is we take our AST and we do a well-formedness check on it. We do a well-formedness check on it. That's one source of errors from our compiler, right? Our compiler might find a duplicate identifier or an unbound identifier, and we report it at that point. And the other place we might get an error is by doing some comparison and then doing like a jump to not a number. And those are really the two sources of errors in our compiler. And I want to make an observation about this. I mean, aside from parse errors, once we have the AST, those are the two sources of errors. And I want to make an observation about this. In well-formedness, we made a decision. Every time we added a well-formedness error, the well-formedness sort of assumption is that some programs are not fit to run. Sort of a value judgment about them, right? But if there's an unbound identifier in the program, we don't even want to give meaning to that program, right? We refuse to compile it. We could have made a different decision in the language, right? We could have decided that an unbound identifier means false, something like that, right? If you look it up in the environment and it's not there, it means false. And we could pick that duplicate IDs in let bindings have some meaning, right? We could always give meaning to some of these things. But we decided that some programs are not fit to run because for some syntactic reason or because we didn't want to ascribe meaning to it, we were just going to reject it outright. That's the assumption we made in well-formedness. And then we said everything else gets through, gets compiled, and then it might produce these other errors at runtime like not a number, not a bool. Now, there's some other programs we've seen this quarter that seem, and some of you have said in written assignments or said in different times in lecture, that they are also not really fit to run. This program, like adding one and true in our language, it's kind of obvious to us that this program isn't going to be very productive to run. Now, in terms of optimizations, which we've been talking about for the last week, right, if we want to keep the language the same, if we don't want to change the language, we need to compile that to something that throws an error. The programmer might have been expecting that to throw an error. So we need to compile it, it needs to run, and then it needs to throw an error. But if we want to make a different design decision, we wanted to make a different design decision on behalf of our users, we could say, well, it's totally reasonable to take the perspective that this program is completely unfit to run. And we could have type checking say, somehow, before running the program, without compiling it, without compiling and running it, we could have the compiler say, well, I'm sorry, but it looks like at runtime, you're going to try to add a number and a Boolean, and I don't want that to happen. Not in my language. Right? Not in my language will we try adding these things at runtime. So the change here is taking this error that could happen at runtime and moving it forward into the compiler, right? We're changing the time at which the error is reported. Now, for a program like +1 true, we could imagine what it would look like to implement this for +1 true. We'd have to do something like, well, we're going to implement something. I mean, we have well-formed and we have compiled, so it seems like we're going to have some new function that we write called type check. It's going to have some arguments. and it's going to have some return type. And when I introduce things like this, I like to think about how we would go about doing things like this in our implementation on simple examples, and then start to scale them up to other examples. So let's think about the type checker and what it would mean to give this kind of error message. Let's get a feel for what this function would look like if we tried to add this new stage to our compiler. What do you think the inputs and outputs to the type checker are? Let's start with the outputs. What do you think the output of the type checker is? What's the output of the type checker? Output of the type checker. Go ahead. Maybe a type, right? Ooh, maybe it outputs something that's a type. So that I don't confuse this with the OCaml keyword type, I'm going to call it a tip. Because type, if I wrote that in an OCaml file, it would be like syntax error. You can't write type here. Type is a keyword, so I'm going to write tip. So maybe it's some representation of a type in our language. Maybe that's what it returns. Other options for what TC might return, have as a return type. Yeah. Maybe a string list of errors. Maybe a string list of errors. That actually matches well-formedness well. Well-formedness comes back with a string list of errors. What other things might it return? Yeah. So either errors or you're saying the expression itself. So some kind of a string list, exper, either one of those. Other options? So for the sake of starting this, I'm going to pick one of these. I almost want to do choose your own adventure with a clicker question, but I think it'll be interesting to pick this one first. So let's say we want to make the type checker like well-formedness, right? Well-formedness returns a string list of errors. We can collect all the errors and return those to the user. Okay, so the type checker is definitely going to have to take in an expression, right? That's sort of clear that it's going to take in an expression. And let's start with that. It's useful to start with that and then see what other information we might need. And we can start with this simple case. So we're going to match exper with, and if we have an e'2 of e plus with a e num and an e bool, that produces cannot add. Can't add number and bool. Cool. What's going to go wrong as we try to generalize this? This is a super specific case. Okay. What's going to go wrong as we try to generalize this? Say we take a less specific case where we have an e plus, and we know the left-hand side's a number, but we don't know what kind of expression is on the right-hand side. What's going to go wrong here? I mean, is there an error? You don't know, right? We need to know something about E2. We need to know something about E2. Okay? If we do the recursive call on E2 and get back a list of errors from E2, well, maybe there's an error in E2, so like, there was an error there. We don't need to worry about what's happening in this plus. There was an error in E2. But if there's not an error in E2, we need to know more about E2 to know if this is okay. We need to know E2's type, right? What was the other answer? Someone said something other than type. If it's a number. We need to know its type and know if it's a number. Right? So it turns out that representing types here is actually pretty important. And in fact, while this specific case is kind of cute for an example, this doesn't help us much with understanding what's going to happen in a real type checker. Right. So it's kind of a cute example to do this for the really specific case, but this isn't very helpful for understanding what a type checker actually needs to do. So let's think instead about the more general cases. We have E1 and E2, and let's return a type. Let's return a type for now. So let's say we do this. We can say let T1 equals TC of E1. I'm going to leave some space because we might need more arguments in a minute. TC of E2. Okay. And now we need to decide what a type is, right? If we're going to take the type for E1 and the type for E2, now we have to start building up a representation of these types, right? That's something we need in our compiler, is what the heck is a type, so that we can do comparisons on it and ask questions about it. So let's think about that. What are we going to have as our definition? Oops, not let. Type tip is going to be, what are some things that we could have as types in our language? What are some things that we have as types? Just shout them out, shout them out. Numbers, what else? Booleans, what else? Tuples. All right, so we've got num, bool, and tup. Those are the three types in our language. We have numbers, booleans, and tuples, right? So to get started, it seems like this is a reasonable way to approach this idea. All right. So for this e'Prim2 case, if we know we're doing an E+, right, we can ask are T1 and T2 both num-type things? If so, what's the answer for this case? What's the answer for this case? If both are num-typed things, what's the answer? Empty list. There's no errors. No, it's some type? Which one? Number. So this case not only checks that the types of the left and right hand operands are numbers, it calculates the type of this expression, right? So the type checker is doing two things at once here. It's both checking that this operation will work and calculating the type of this expression. Those are the two things that the type checker is going to be doing in every case. And if it's anything other than number and number, right, anything else, could be a tuple and a boolean, could be a boolean and a number, any other combination here is going to produce some kind of error. Now, we could try to represent the errors in the return type, right? We could have some type for the return that's either the calculated type or some errors. We could do some representation like that. For simplicity in class, I'm just going to have this directly fail. So we're going to calculate a type, or we'll fail with some specific error. Right. Which is, in this case, that we can't add if one of the operands isn't a number, we can't do the addition. And we could start to generalize this to other cases, like doing this for equality, like the operators. We can see just by looking at what tag checks we would have done, what types we require for the different operators. We can start extending this case. Okay, okay, so let's put this in parentheses for a minute, because we might want to write a match next. And I want to direct your attention to this next example that's here. So this is a function. It's called abs value, so presumably trying to calculate an absolute value. There's something wrong with this function, I'd argue. What's wrong with this function? Yeah. So you're pointing out there's a use of x here that seems to expect it to be a number, and there's a use of x here that seems to expect it to be a Boolean. X is used inconsistently here. X is used inconsistently here. Now, because I named this function absolute value, I made you expect that x should be a number. If I named this function something else, if I named this function something like if true else number or something like that. Something that suggested that maybe x should be a Boolean, we might complain and we might say, well, x is correctly used as a condition and returns itself in the then case, but it's incorrectly used as a number in the else case because we're going to try and multiply a Boolean. It's an interesting problem because we don't know really which one of those uses of x is a mistake until we see what the intent was of calling abs value. How do we usually solve this? What have you seen in languages you've used for how to express this intent? Or how to express this intent? Yeah. So an error message you see, right, will be, I expected this type but got some other type. What do you write in your program to express this intent? What have you written in a program to express this intent? We write a type for x, right? In Java or C, we don't just write the parameters of functions as their names. We write a parameter accompanied by the type that it expects. This allows the compiler to look at the body of the function and say, here's what the programmer is expecting these values to be. I can type check the body assuming that. And later, when the function is called, we can check that it's provided with the right kind of arguments. But it's really important for type checking a function in isolation that we know what the programmer intends for all the arguments to be. If we don't know what the programmer's intent is here, it's a much different problem to figure out what type is reasonable for x. We actually can do it. You can infer this from the context. But in almost all systems, there is at least a way, whether it's the default way or not the default way, to write down in the syntax of the language what type we expect for parameters. What type we expect for parameters. And this is done primarily to make the compiler's job easier, or in some cases possible, when type checking functions in isolation, they're going to be used somewhere else. Okay? So that's interesting because that means it means a few things. It means, first of all, we need to think about tcdef. Right? There's going to be a function we write that type checks function definitions. It takes in a D that's a function definition. And it means that our definitions need a bit more information. So let's just think about like the one argument case to keep things simple, right? There's going to be a name for the definition. There's going to be a argument, and then there's going to be a type for the argument before the body. This is now part of the abstract syntax of the language. We wrote it in the concrete syntax just now, and this would need to show up and be available in the abstract syntax, and now we can work with that. Okay. So when we do a tcdef, what do you, actually, this is worth just thinking about and talking about for a minute. What's the body of tcdef going to look like? How are we going to type check? I mean, we need to type check the body somehow. What's the body of this case in tcdef going to look like? What are we going to do? Talk about this for just like 30 seconds to a minute. What are we going to do here in order to type check this function definition? Okay, so suggestions for what we should do to type check function definitions now. What should we do to type check function definitions? Go ahead. So you're saying something about the environment. So something's going to happen here where we need to think about the environment. What needs to be in the environment? How do we represent this? Yeah. So we need to have the IDs and the types associated with the IDs. What else needs to change? I mean, we're going to write some code here. What else needs to change? Where does this environment go? I don't see environment anywhere. Is environment another argument here? Another argument to tcdef? Yeah. So you're saying TC up here, right? TC needs to take in some sort of environment, right? Maybe let's call it the tip end. Right? And that is going to be a mapping from names to what types they have. Just like our compiler is a mapping from names to what stack location they're at. And well-formed has a list of IDs for what's in scope so that we can report unbound identifiers. We can have something that represents what types there are. And so here, what we need to do is type check the body. We need to type check the body. And the environment we type check it in needs to be the argument mapping here. And then when we get to EIDs, when we get to the EID case, now we can do the thing we're used to doing where we look up in the current environment what the type of this thing is. And if it's there, that's the type of the ID expression. Otherwise, it's an unbound identifier. So well-formedness would have caught it, or we can report an unbound identifier here. But this gives us a way to connect any definition of an argument or any definition in a let with the type that it had when it was defined, and then we can look that up later. So now when we're type checking this if, right, this is going to say x is expected to be a number as we go into the body. We have to imagine the if case, because the if case isn't on the screen. But the if case can get the type of the condition and then check if that is a Boolean or not. In this case, it'll be a number. And we can get from the type checker an error that says the condition part of this is a number and it was expected to be a Boolean. We can get that just by inspecting the AST rather than running the program to figure that out. Okay. Oops. So next example is, let's imagine we fixed this, right? So the previous version of this had the bug. But let's imagine we fixed this and made this actually be a working, oops, let me keep that on screen, sorry about that. And made this be a working version of absolute value. But then somewhere else, like down here, we call it incorrectly. Somewhere else we call it incorrectly. Call it incorrectly. We would like this to say, right, the error message that was suggested earlier is sort of directly relevant here. Someone suggested the error message of expected a number but got a Boolean, right? That kind of error, that's the kind of thing C and Java tell you, and the kind of thing OCaml tells you. Okay? And so the mismatch here is between this true and this x declared as a number in absolute value fixed. Where would this show up in the type checker? Like, what case would be added to TC that would talk about this? Yeah. So there'd be an EAP case in the type checker because this absolute value fixed call is an EAP expression. So if we think about this case now, we're going to have some EAP case to worry about in the type checker that has a function and the actual argument expression that we need to evaluate. So there's a little break here. This is continuing the TC function. So there's an EAP here. What do we need to know in order to type check this? I mean, we can definitely get the argument type by type checking the argument expression with the current type environment, right? We can definitely get that type. Then what do we need to know? What should I be checking? What should I be checking about argt here? What should I be checking about argt here? Yeah. Ooh, find the function definition in defs. So and I'm just going to put this as a, you've done this before in well-formedness. When did you have to do this in well-formedness? What error was related to finding the function definition? What error is related to finding the function definition? When did you have to do this? For arity checking, right? So when we wrote well-formedness for Cobra, right, when we introduced functions, you'd have to find the definition in the definitions list and then compare the number of functions at the call site to the number, the number of arguments at the call site to the number of arguments in a definition, and that could be an error. Here, instead of just comparing the number, right now I'm doing this with just single argument functions, but instead of comparing with just the number of arguments, we need to compare the types of the arguments. We need to compare the types of the arguments. So if we have, if we do find the definition, then again we'll have a def that has a, and we all, actually all we care about here is we don't care about what the name of the function is, we don't care what the name of the argument is, we only care about what the type of the argument is. And we need to make sure that what we get back, right, or sorry, we need to make sure that what we pass in, argt, is equal to t. We need to make sure that argt is equal to t. So we can finish this off by checking if these things are equal. Argt is equal to t. Oh. Is that a good end to this? Like if I really just stopped here, right? I'm not sketching the body of this def case. If I said, well, the result of type checking this is true if the argument is equal to the argument type, the one on the definition, and it's false if they're not equal. What problem would that have? Problem would that have? Yeah. So the type checker says that we need to return a type. We're both checking that things are used consistently and calculating the type of the current expression. There were these two jobs that the type checker had. We can check if these things are equal and give an error if they're not, right? So it's definitely the case that we should make sure that if these are not equal, right? If they're equal, then we want to do something. If they're not equal, we definitely have an error. Right, and this is the error message that was suggested earlier of you passed in a Boolean and a number was expected. But what type should we return? Do we return argt? Is argt the type we return from this whole thing? What type should we return from this? Suggestion? Yeah, go ahead. Yeah. Maybe we should type check the body, right? Maybe we should type check the body. So that's cool. So that means that we should add something else in here. Maybe I can make a little space. Oops. I just want to get this idea written down and write it in a different color. So idea. Somewhere in here we want to do TC of body. And here, let's pattern match on body too, right? Because we needed body. And we know that when we type check the body, we'd get back some type for the body, and that would be one thing we could return as the type for this whole thing. That might make sense. So maybe we're going to do some type check on body. Okay. Other suggestions. Other suggestions. Yeah. So your suggestion is keep track of a mapping from function name to return type and pass that around. And then when we get to this case, we can just look up the return type of the function. Is that the suggestion? So I think you're suggesting adding this to the environment, right? Or having another environment that tracks the return types of function definitions somehow. I see. So you're saying you want an environment that talks about not just the function's argument types, but its return types as well. Like add that to the environment information about a function. Interesting. Okay, let's call this idea. Any other ideas? Any other ideas? Yeah. Uh-huh. Uh-huh. Mm-hmm. Yeah. Yep. Yeah, so let's keep everything about function definitions the same, except right now we've added the ability to put these types on arguments, these expected types on the arguments. Oof, I mean, I don't know. One of these maybe one of these ideas, I don't know. All right, which one of these do you want to pursue? Which one of these do you want to pursue? Okay. 5, 4, 3, 2, 1. Okay. Talk about this for a minute. Talk about either problems or reasons that one of these might be good. Talk about this for a minute. It's a useful one to talk through. Okay, click in again after chatting about this for a minute. Five, 4, 3, 2, 1. Okay. All right. So let's just scoot this down for a sec. The one thing that got worse when I switched the drawing program I used this quarter is that I lost lasso select, which is my favorite tool. But this program makes such better PDFs. So we could say that let the return type is equal to TC body. What environment should we use for type checking the body, by the way? We're doing TC body. I left it blank. What environment should we use? What environment should we use? We have to pass in an environment when we type check the body. So what should we use? Yeah. Pattern match on some input. So you want to actually grab the X here. Have I used X? No. Okay. So you're saying use X and then T or argt? Should be argt. Should be argt. So we want to type check the body. In this case, we type check it by passing in Boolean, right? Because Boolean's the type of the argument expression, right? If we think about this program, there's two functions here. There's absolute value fixed, and there's absolute use absolute value. We have this app case, and then up above we have this type checking the def case, right? So we'd presumably, much like well-formedness, we'd type check all the defs, right? And that would lead us into type checking the expressions in the bodies of those definitions. So what do we use when we type check the def? When we type check the def, we use the provided expected argument. So if we use argt, we're saying, oh, don't worry about what your function expected to get. Let's type check it with what we gave it. You see if that works out. Seems unlikely to work out, right? Because if there's a mismatch there, right, if there's a mismatch between the type, so maybe we should just pass in t, because it seems weird to pass in the argt. It seems weird that you pass in a type that it might not be working, because we've already checked. So maybe we pass in t. All right. And so then here, here we would just write the return type, right? The return type is what we return if they're equal. Right? So that would work for this program, actually. If we think through what would happen, we'd say, here's true. That has type bool. We'd go type check the body. The body's return type would be number, but then the arguments wouldn't be equal, so we'd fail with bad argument type. We'd fail with bad argument type. And that's what we would hope would happen in this case, right? Is that we'd get the error that the argument wasn't equal to the declared argument, so that's a bad argument type. All right, let's look at one more example. Let me keep this little eApp implementation on the screen. Yeah. Yeah, it's like we redid some work a little bit. So the comment was, well, basically that same thing is what we did to type check the definition. So there's this lurking unease that we're redoing work somehow. And it's like, well, we did that before. It seems a little odd. Let's look at one more example. Okay, let's press on. Let's press on. We've made a decision. Let's see how it plays out. I mean, just to be clear, you voted for this. Okay, so I'm not just picking something. All right. So you voted for this after discussion, before and after discussion. I think as a group, you became more into this idea after discussing it. All right. One person changed. Okay. No one changed their minds. All right. Okay. All right. So let's press on. So here's up to, and up to is one of these things that sums up numbers from n down to 0, right? We've written this kind of sum before, just to give an example of a recursive function. And I put a false in the then case, just to be clear that there is going to be some error in this program, right? All the programs I'm giving today have some kind of error in them. So let's see. So let's think about type checking this. We'll type check the definition first, because we're going to run our type checker by type checking all the definitions, the same way we did well-formedness by checking well-formed of all the definitions. We'll type check the body of up to with an environment where n is num. Okay. We'll type check the if, which means we have to type check the condition, the then, and the else branch. Let's focus on the else branch. I think that's the most interesting. So in the else branch, we have a plus. We'll look up n, and n is a number, right? So we're sort of good here. N as type num. Let me draw that with a colon, because we've been using colon, right? N as type num, so that seems good for plus. Then we get to type checking up to, and this is an eApp, so we get to think about this code here, right? Because up to is an eApp. The argument is a minus expression, so we should know that's going to produce a number. So then we type check the eApp. The eApp calculates that argument type and gets a number for this part. This part is number. And then we look up the definition, we find up to, and we type check the body of up to with the argument being a number. That's this part, right? Okay. So then we're going to type check this we're going to type check the body of this definition in an environment where n is a number. We have to type check an if, which means we have to type check the condition to then in the else branch. The else branch is probably most interesting. And so there's a plus. And we know that n is a number from the environment, and then we have this EAP. So we're going to have to look at the EAP case. So in the EAP case, we calculate the type of the argument. Okay, yeah. This is actually really, really interesting and important. Java type checks every method's body once. Java does not type check every method's body once for each method call to that method. The type checker, most type checkers where annotations are provided or types are provided with like a colon or a type declaration, are emphatically linear time in a number of definitions in the program. They might do a little more complicated work in the body of a method to figure some stuff out, but they visit each function or method once. If they didn't do this, you would be fairly unsatisfied with the performance of Eclipse. If Eclipse was doing like a different check for every different invocation of a method, right, that actually was related to the size of the method, it would get really bad to type check Java really quickly, right? You'd have this, you'd have this at least kind of quadratic in the number of methods times number of invocations of the methods problem going on. And it would just take the type checker a long time to complete. So this idea of trying to type check the body again at a call site is a bit of a non-starter. You could have run into the same problem in well-formedness, right? In well-formedness, when you look up the definition, all you check is the arity. You don't try to check the well-formedness of the function body when you get to an EAP in well-formedness. You may have had an infinite loop bug like this when you first implemented well-formedness. So this idea of doing another type check at an application is a non-starter. So it turns out the thing we should do here, and actually this surfaces a bit in recursive functions, is we don't just need to know what the types of all the arguments are. In this recursive case, we actually have a bit of a problem. We need to somehow know, without checking the body of up to, what the return type of up to is. Somehow we need to know, without type checking this whole body, without calculating the answer for this whole body, we need to know what return type we're going to get when we call it, because that's part of the body. So what we need to do, or at least a way to solve this problem, there's different ways to approach this, but one way to solve this problem is to add the other kind of annotation or type declaration you're familiar with, which is the return type declaration. Right? This is what return types are really good for. It's particularly the recursive case where return types are incredibly useful. Right? Because if you have something recursive, you need to sort of know its type to type check it. Right? You can't type check its body without knowing something about its type. So if we add a new kind of annotation, that's the return type annotation, right? Now, our definition will expand yet further, right? We won't just have a definition with the argument, the type of the argument in the body. We'll have the argument, the type of the argument, the type of the return value, and then the body. But if we do have that information, then we don't need to re-type check the body to calculate the return type. We can just give the return type directly. Just give the return type directly. Actually, let me do what I did above, because I think it's a little more useful for the notes. Let's gray this out. And then add TR here. So this is where we see the sort of assume guarantee reasoning we talked about when we first talked about functions. When we type check the function, we use the assumption of its argument